Hi everyone, today we're going to be going over Lacustrine depositional environments, otherwise known as lakes. First, I'm going to start by going over some different classes or types of lakes. The 5 main categories of lakes, which are shown here, include volcanic crater lakes, man-made lakes by dams, oxbow lakes, and glacial and tectonic lakes. The majority of modern lakes, about 90% of them, are of tectonic or glacial origin. Throughout this lecture, we're going to be going over in more detail different classifications of lakes. For example, we're going to be talking about what temporary lakes are compared to permanent lakes and their characteristics, like being underfilled versus overfilled, as well as balance filled. And then we'll also talk about closed versus open lakes, saline versus freshwater lakes, as well as evaporative lakes or playa lakes. And we'll also go over trophic differences, which we'll define later. And these include classifications oligotrophic, mesotrophic, and eutrophic, which have characteristics listed here that we'll go over later as well. But first, let's go over what factors control lacustrine sedimentation. These factors include, but are not limited to, climate, geography, tectonics, basin form, hydrology, composition of the country rock, and the nutrients available. So now to get into more of the classifications we were talking about, we'll talk about open and closed lakes first. And this has to do with the physical and chemical processes that control lake sedimentation. So for example, an open lake is one in which inflow and outflow occur, and the annual inflow to the lake plus the direct precipitation, so everything going into the lake, rain and river input, is greater than or equal to everything going out of the lake, or outflow plus evaporation. And so this means that open lakes are balanced or overfilled. If the input, inflow plus rain, is greater than the output, or outflow plus evaporation, then it is an overfilled lake. However, if they are equal, it is a balanced filled lake. And this characteristic is actually really important for determining the water chemistry of the lake and the type of life that can live there, and a lot of other characteristics of the lake. For example, for overfilled and balanced lakes, these lakes are typically freshwater lakes, and they have a stable lake level. However, when we have closed lakes, these are typically saline lakes or not freshwater. And this is because closed lakes are defined by their input being less than their output. So the outflow plus evaporation is greater than the inflow and precipitation, causing the evaporation of fresh water and leaving behind minerals that precipitated out of solution upon evaporation. And this leaves a really salty lake. Some examples of open lakes versus closed lakes include the Great Lakes are great examples of open lakes. They have input that exceeds or is equal to their output. And the Great Salt Lake in Utah is typical of a saline lake where evaporation exceeds the input. Now we'll go into some more lacustrine processes. One important process is called mixing. Lake mixing of surface and deep waters can either occur or not occur depending on the size of the lake, the depth of the lake, the wind in that area, the climate in the area, the temperature and salinity of the lake water, etc. And this creates a variety of scenarios which include monomictic, dimictic, polymictic, and meromictic lakes. This classification system of lakes is dependent on the amount of times a lake will go through a mixing phase annually, or the lack thereof. So for example, monomictic lakes go through one phase of mixing annually. Dimictic lakes go through 2, hence mono versus di, and then polymictic lakes go through many phases of mixing throughout the year, which is most common in shallow lakes because shallow water is more likely to be less stratified, meaning more well mixed, than deep lakes where stratification can more easily occur. For example, in really deep or saline lakes, what you'll have is permanent stratification where mixing never occurs or rarely occurs, and this is called meromictic lakes. This happens because the salinity and temperature differences cause a density difference in the deep water compared to the surface water, where the deep water is really dense or cold and saline, and the surface water is a lot less dense because it's more fresh, less saline, and it's warmer. And this causes a permanent thermocline or chemocline or both in a lake that causes it to stay meromictic. And something that permanent stratification will often cause is oxygen depletion in the deeper water of the lake. This is because without mixing, oxygenated surface waters won't reach the deep waters, and deep waters will become oxygen depleted or even anoxic, meaning in the absence of oxygen. And in these anoxic zones, the formation of something called redox stratification can occur. This is typically once you get down into the sediment, because it's not often that the water column is anoxic enough for this kind of stratification to occur. But once in the sediment, stratification of metabolic pathways dependent on what electron acceptor is available in that zone occurs. And this stratification includes metabolic pathways going from oxic respiration or aerobic respiration, and then below that, where it's anoxic, you'll get nitrate reduction, manganese reduction, iron reduction, sulfate reduction, and then methanogenesis, respectively. And I talk about this in more detail in my redox stratification video. So if you want to learn more about that, you can go there. But basically, this can occur in stratified lakes that are meromictic and don't undergo mixing that often. Now, other than oxygen content, salinity can have a huge effect on chemical composition of a lake. And I list here dilute lake compositions compared to that of saline lakes. In dilute lakes, or very freshwater lakes, you're going to get cations that commonly include sodium, calcium, sometimes potassium and magnesium. And if there's limestone or dolostone country rock, you can get carbonate ions. And if there's oxidation of pyrite or weathering of gypsum and anhydrite, you can get sulfate ions, etc. And common mineral precipitates in dilute lakes include carbonate minerals, minerals linked to redox conditions, which we just talked about, such as iron and manganese oxides, depending on how intense the stratification is in the lake, and some clay and phosphate minerals. Alternatively, in saline lakes, mineral precipitates commonly include evaporites. Evaporite minerals include calcite and dolomite, which are calcium carbonate and calcium magnesium carbonate minerals, respectively, gypsum and anhydrite, which are calcium sulfate minerals, halite, which is just salt, NaCl, and then potassium and manganese fluoride salts last in the order going from least to most soluble. So therefore, the order in which these evaporite minerals are listed on the slide is the order in which they will precipitate out of solution. Now we'll talk about trophic levels. Trophic levels also have to do with the chemical composition of the lake, and in terms of human use, matter a lot for the health of the lake and whether it is usable fresh water. Trophic levels include oligotrophic, which is shown here on the top, with clear and well oxygenated water with low biological productivity, and then mesotrophic in the middle, which is kind of a transition between oligo and eutrophic, and then we have eutrophic levels, which are characterized by mucky water with high biological productivity and very low oxygen content. Lakes start as oligotrophic and can eutrophy throughout time. This is a natural process that occurs in lakes if they exist for long enough. However, this natural process takes tens of thousands of years, but today, with humans around and our horrible extreme pollution habits, we are causing lakes to eutrophy in tens to hundreds of years rather than tens of thousands of years. This makes lakes less habitable an environment for aquatic life and also limits how much water we can get from that lake. Here's an example of a beautiful picture of Lake Superior, which is an example of a healthy, clear, bright, oxygenated, oligotrophic lake. And then on the right, we have an example of eutrophic water in this river in Washington, D.C., where we have a dense bloom of bacteria causing high biological productivity and low oxygen content. Now that we have some of the main processes that control lake chemistry out of the way, let's talk about some of the physical body parts of a lake system. Lake facies include sands deposited at the mouth of rivers, which empty into the lake and along the shoreline, as well as muddy facies on the deep bottom lake. Different body parts or landforms associated with lakes include the shoreline, deltas and fans, central basin or offshore environment, and basin floor fans. And the basin morphology, or shape of the basin, plays a large role in the distribution of the facies across the lake. For example, the basin slopes, depending on whether they are shallow and gradual or abrupt and steep, this will cause distribution of facies throughout the lacustrine system to be very different in different lakes. So first, let's start with lacustrine shorelines. Lacustrine shoreline type depends on slope, like we just talked about, energy levels in the littoral zone. The littoral zone is the one shown here and here. It's basically where the shoreline occurs, and then the rest of the lake in the middle part is the pelagic zone. And then the last factor that shoreline type depends on is type, supply, and texture of sediment. The first shoreline type we'll go through is a siliciclastic shoreline. Siliciclastic shorelines can include high energy sandy beaches that produce well-defined laminae in the littoral sands, and these are typical of large lakes. However, another type of siliciclastic shoreline can include coarse gravel sorted by longshore currents caused by strong winds, and this is typical of small elongate lakes. The outcrops shown here in C and D show the two types and their differences in stratigraphy when seeing them in an outcrop. We can see the well-defined sand-rich laminae in C is very different than the coarse-grained massive structures seen in D. The second major type of shoreline that we're going to be talking about is carbonate shorelines. Carbonate shorelines can form when a shallow bench or ramp environment provides the perfect conditions for carbonate precipitation. Shown here in the pictures, we have an example of a bench type carbonate shoreline, which is typically a large shallow area that cuts off more abruptly than a ramp type carbonate shoreline. And this shallow carbonate bench can either be high or low energy, which causes different types of carbonate precipitation. For example, high energy carbonate bench environments could cause ooid formation, whereas low energy carbonate bench environments can cause more carbonate mud precipitation and accumulation, etc. And then we have carbonate ramps, which are similar to carbonate benches but slope more gently down to the main lake basin. And these two can either be high or low energy, causing differences in the type of carbonate precipitation that occurs there. Now getting into the deltas and fans in lacustrine systems, styles of delta sedimentation in lakes depends on the density of the inflow water versus the lake water. When the inflow water and the basin water match in densities, this is called a homopycnal flow. And this is typical when you have high bed load and dilute lake water. However, when the density of the inflow is less than that of the basin water, you have a hypopycnal flow. And hypopycnal flows are typical of dilute inflow into saline lakes. And this causes sediment plumes at the surface or from the interflow if the lake is stratified. And lastly, if the inflow density is greater than the lake water density, this is called a hyperpycnal flow. And this is typical of high suspended load into dilute lake water. All of these different types of flows cause different types of sedimentation in the delta or fan facies of the lacustrine system. For example, you can see that in the cross-section cuts of each one of these figures, there is different stratigraphy. For example, the top homopycnal flow figure shows the lakeward progradation of the system caused by the homopycnal dominant flow, and then you've got aggradation and slow progradation in the hypopycnal flow regime, and clay flocculation settling from suspended sediment plumes in this regime as well, causing graded bedding. And then you have aggradation and slow progradation again in the lower hyperpycnal flow regime. And then you have probably the most easily recognizable characteristic of hyperpycnal flows, which are turbidites. Turbidite sequences will be talked a lot more about in the delta and the submarine fan video. So you can watch those to learn a little bit more about turbidite sequences and why they're so easily recognizable. Now we're going to go over open water facies. So we'll talk a little bit about rhythmic laminae, the lamination that occurs in open water sedimentation, which is caused by winter ice mud deposits and the coarser deposits during spring runoff respectively. And we'll talk a little bit about the paleoclimate implications we can take from certain lake sediment, such as shale, which is typical to anoxia, etc. But first I'm going to show you on this figure, which includes a lot of different facies and processes that occur in lacustrine systems, causing different types of deposition and sedimentation. On this figure, we can see the different types of inflow that we just talked about. We've got the densest inflow, which is the hyperpycnal flow. Then we've got the homopycnal flow in the middle and the hypopycnal flow on the top. Then in terms of nutrients, you have volcanic ash particles, you have aeolian particles, aerosols, etc., bringing nutrients into the lake system. Then you have dropstones from ice causing deposition of dropstones in open lake laminae or varves. Then you have littoral zones where you've got vegetation, erosion occurring, etc. You have rain input as well as the inflow we already discussed. And down here in the sediment, you have erosion, reworking, bioturbation, and early diagenesis, which may modify the rock record. And here I added the ichnofacies, which are trace fossils common in open water lacustrine facies versus littoral zone lacustrine facies. We've got Murmia, which is a type of ichnofacies or trace fossil common in the open water, and then we have Scoenia, common in the littoral zone of lakes. Moving on to some real-life outcrop examples of the laminae from open water lake deposition. First, we have this example of bedded silt, sand, and clay from late glacial outwash deposits in the Kamloops Lake of Canada, which has an indicated tuff layer in it as well. You can see now the input from volcanic sources. Additionally, we have this next example where we have laminated diatomaceous siltstones of the Miocene Mytilene Basin in Greece. Diatoms are tiny microscopic algae that have calcareous chambers or skeletons or shells, whatever you want to call it, and their skeletal parts accumulate in the bottom sediment and cause fine layers of highly diatomaceous lake sediment. Then we have this example of organic rich lacustrine shales deposited in a meromictic alkaline lake that have been altered to zeolites by saline alkaline pore fluids. This is from the Miocene Aurora Formation in the Kenya Rift Valley, and like we said, shales are typical of anoxic environments, and in this case we already see that it says it's a meromictic lake, which makes sense that it was probably stratified and oxygen depleted in the deeper parts of the lake where sedimentation was occurring. Lastly, we have this example of lamination in black shales of the Jurassic East Berlin Formation in the Hartford Basin in Connecticut. And in this figure, we can see the white laminae are carbonates and the dark laminae are clays. And this occurs typically in lakes that are located in environments where seasonal changes can cause differences in lake sedimentation. For example, during colder winter type weather, you've got ice cover that causes only mud precipitation from suspended particles settling down onto the lake floor, which typically causes very thin, fine-grained laminae of dark, muddy sediment. Whereas in the warmer spring weather, where you have runoff occurring and inflow, bringing coarser-grained sediment into the lake, you have coarser, lighter sedimentation occurring, causing lighter layers in the lake. This is typical, a lot of rhythmic lake laminae, but in this example particularly, it shows an accumulation of organic rich mud, and this in particular is a precursor for carbonaceous shale and oil shale, and these can be precursors for fossil fuels. Now getting into saline lakes, mudflats, and pans. We have here a model of closed basin sedimentation where there is a distinct separation of facies, including the dry mudflat and the saline mudflat. In the dry mudflat over here on the strat column to the left, we can see it includes a lot of mud that has a lot of desiccation cracks indicative of dry mudflat areas, whereas the saline mudflat also includes a lot of mud but less mud cracks. And then we've got the saline lake or saline pan, where you have mud laminae precipitation with evaporite precipitation, etc. And so an example of the evaporitic deposition that occurs in the center of these types of lakes is figure F, where it shows bedded chronocycles from the center of the same lake that we're showing in all the other pictures. And the arrows in this figure indicate thin detrital layers overlying corroded salts that are linked to the dilution of brine during the rainy season. So what you're seeing is the evaporitic season with the huge evaporite crystals forming due to the evaporation period where all of them are precipitating out of solution. And then you have the upper evaporitic deposits from the previous dry season being redissolved during the next rainy season to a point, causing this darker brown dissolution layer where it basically marks the boundary between the previous and the next dry season. Lastly, we'll go over lake stratigraphy and point out some typical characteristics of each type of lake shown here, including overfilled, balance filled, and underfilled lakes. Like we talked about, we have open lakes, which can be either overfilled or balance filled, and then we have closed lakes, which are underfilled and typically saline. So let's talk about each one of these in detail regarding their characteristics and their stratigraphy. What you can see in the strat column of an overfilled lake is very coarse sediment, typically because the inflow of sediment-rich water is occurring very often in these types of lakes, and the sediment plus the water supply is greater than the accommodation space or basin area, causing really coarse-grained, thick deposits. And the hydrology in these basins, like we already discussed, is open, where you have open inflow and open drainage or outflow, causing this lake to continuously be resupplied with new water and new sediment, and therefore stay pretty fresh and well mixed. This type of lake occurs in all climatic zones, but is rare in arid or dry climates. And the lithologies seen in these types of lakes, as we can see in the strat column, include sandstone, siltstone, mudstone, carbonates, and coal. And hydrocarbons that can occur in these types of lake sediments include oil and gas and waxy low sulfur oils. Additionally, the abundance of ichnofacies is high in these types of lake sediments, and like we already said, the salinity is low, it's very fresh water, and the lake level is stable because of the open drainage, and the stratigraphy is progradational because of the high supply of sediment. Now moving to the balanced filled lakes, what we have in these lakes is a sediment and water ply that is equal to the accommodation space, and so the hydrology in these types of lakes can either be open or closed to drainage, meaning periodically imbalanced inflow and outflow to create an overall long-term balance. So sometimes this lake may be closed and the outflow is greater than the inflow, and sometimes it can be open and overfilled where the inflow is greater than the outflow, but overall it creates a long-term balance. And the climate in which these lakes occur is any climate, and lithologies that are common in these types of lake sediments can include sandstone, siltstone, mudstone, carbonates, marlstones, and sometimes evaporites and coal. And hydrocarbons common in these lake deposits include mainly low sulfur oil. The abundance of ichnofacies in these types of lakes is also high, and the salinity can be variable because, like we said, it can sometimes be closed, sometimes be open. Additionally, the lake level can be stable, but also unstable depending on the fluctuations it's going through at the time due to climate. And the stratigraphy is either progradational or aggradational, depending again on whether it is closed or open at the time. Lastly, we'll discuss underfilled lakes. Underfilled lakes, like the saline perennial lakes we talked about, are lakes where sediment and water supply are less than that of the accommodation space or basin area. The hydrology in this case is closed or partially closed to drainage, and this is typical in semi-arid to arid climates. The lithology seen in these types of lake deposits includes sandstone, siltstone, mudstone, carbonates, marlstone, coal, and evaporites. Additionally, hydrocarbons can include oil, and ichnofacies once again are abundant, and the salinity in these underfilled lakes is high, and this is because of their closed basin hydrology. Additionally, the lake level is unstable, and lastly, the stratigraphy of underfilled lakes is aggradational. That is it for today's lecture over lacustrine depositional systems. I hope that this was helpful in learning about lacustrine processes, deposition, and stratigraphy. And I hope that you come back to watch all of the depositional environment videos, and I can't wait to see you there. Thanks again for watching, and I'll see you guys next time. Bye.